Hi, welcome to the Electronic Devices fifth unit lecture. Now, the fifth unit is on power devices and display devices. So, hope you remember me. This is Sheikh Hidayat Basha from RMK College of Engineering and Technology. Now, in the fifth unit, we have the syllabus of power devices, and we are going to see various display devices. So, power devices, we are going to learn UJT, SCR, triac, diac, power BJT, power MOSFET, DMOS, and VMOS. And in display devices, you have LED, LCD, phototransistor, optocoupler, solar cell, CCD. So, in this video, we are going to see the topic only UJT. Okay, so what we are going to see is that in UJT we are going to see the symbol of UJT and its construction and equivalent circuit and intrinsic standoff ratio, which is very important topic, and relative problem we will see on intrinsic standoff ratio and its operation, UJT operation, its characteristics and application. So coming to the symbol, so we can see, so UJT, so as I told you, I will be repeating it. UJT is Uni Junction Transistor. It is a three-terminal device. So you can see the symbol of UJT. It is a three-terminal device where it is emitter, base 1 and base 2. Okay, and it has a single PN junction. So UJT has single PN junction. So I'm repeating again. UJT is a three-terminal device where the three terminals are emitter, base 1, base 2. Okay, and important thing to remember that the emitter should be bending towards the base 1 base 1 terminal. Is that okay? Now, and then next we will see about the construction and its equivalent circuit. Now you can see its symbol. So as I told you, so three terminals, emitter, base 1 and base 2. And if you can see the construction, base 1 and base 2 is connected through a channel, n-type channel, and you have an that is an n-type channel which is lightly doped, and we have a p-type material being inserted in the channel, and we take through the ohmic contact and we make an emitter terminal. So here three terminal. Now this is a complete construction of UJT. So in the construction we take a channel and then ohmic contact, we take the two contacts and then it is as base 1 and base 2, and in this particular channel we are going to etch a well and then we are going to inject the p-type material, p-type semiconductor material, and then it forms only one P and N junction. So one PN junction, and to that particular P we are going to take that terminal with the ohmic contact, and it is an emitter. Now coming to the simplified equivalent circuit. Now this particular symbol can be replicated with a diode representation. So where we take an emitter followed with the P and N junction diode, and it is connected to the base 1 and base 2 channels. Now another interesting point is that the voltage between the B1 and B2, we just try to represent that as VBB. So base 2, base 1 to base 2 voltage, whatever we can able to connect or we can able to calculate. Okay, right. And another important point is that the resistance at base 2 is static, whereas RB1 will be dynamic, it will be varying. Now we will be understanding it better when we see the operation of it. Okay. Now another topic that where we have to learn is that now we will be connecting base 1. Base 1, now base 1 we usually connect to the ground terminal, and B2 will be always positive with respect to B1. That means the voltage at B2 will be higher than B1. And we can see here that the voltage VBB is applied across UJT and B2 and B1. So B2 is biased positively relative to B1. Okay. And another point is that with zero input applied at the emitter, okay, the Now, and if you can calculate the value of your RB1, now this RB1 will give you the value. Now this is your voltage divider rule. If you can apply, you get a formula where RB1 VRB1 will be as RB1 by RB1 plus RB2 into VBB, where VBB is the voltage which is supplied between your base 1 and base 2, right? So this ratio RB1, coming to this point, just make you clear. Now here this RB1 and RB2, now we have taken RB1 by RB1 plus RB2, and this ratio is your intrinsic standoff ratio of UJT. This is very important formula to remember and to do the problems. And another point which you have to learn here is that UJT, the resistance RBB we try to represent as interbase resistance. Okay, and you can see the intrinsic standoff ratio is the ratio of RB1 to RBB, where RBB is the sum of RB1 and RB2. Clear? Right. And then another point here, then now conduction through the emitter terminal begins when the emitter voltage reaches the firing potential given as Vp. So whenever you have the firing potential, that we will discuss about it. So we have the peak voltage, where the peak voltage is given with an equation as eta as your intrinsic standoff ratio into VBB plus VD. VD is the voltage across the diode. Fine. So here, with respect to this, we will see small example problem. You can see here, so intrinsic standoff ratio for the UJT is given to be as considered as 0.6, and if the interbase resistance is 10 kilo ohms, and find the values of RB1 and RB2, so we can solve this problem easily, right, with the formula. Now this will be one of an 4 marks questions or 2 marks question being asked in the examination. And next, coming to the operation. When coming to the operation, we are going to connect base terminals. If you can see, B2 and B1. B2 will be always positive, B1 will be negative. And with the emitter, we are going to give, that is p-type material, this will be always forward bias. So emitter is forward bias, B2 here will be more positive than B1, and this is then circuit diagram of your UJT, and this is your construction diagram. Fine. So next, carrying with the UJT characteristics curve. Now you can see by the curve, you can see that this UJT characteristic has 3 regions. The first one is cutoff region, the next one is negative resistance region, and the next one is third one as the saturation region. Now you can see towards your x-axis we are going to take the current IE, and then towards your y-axis we are going to see the emitter voltage VE, right, and the emitter voltage VE, which we are going to see. Now as we are now at the initial stages, what happen is that when no current is present here, then what happen, there will be only the flow of current will be present through the channel. Okay, and then there will be no current at IE. Fine. So when there is no current at IE, so you don't have a voltage present. Fine. And then at a certain point, when the value, here very important to remember that if the voltage is greater, if the voltage at the emitter is greater than the RB1 and VD, you have the flow of the current from IE to RB1, right? When this happens, when the emitter current is higher, right, what happen is that you can see when the emitter current is happen, it will be the peak voltage. So this will be the cutoff region. So it will be the cutoff region where the current will be very high, right, and then after increasing the voltage, that is, if you are going to increase the voltage of VE, what happen, the voltage will suddenly decrease and the current will increase, right, current of IE will increase and the voltage decreases. Now this is the negative resistance region, and which is useful for the oscillation purpose. Next, coming to the applications, it is used in common triggering circuits, and it is used for oscillating circuits, and very important application as relaxation oscillators.